Please go ahead, Manfred.
Good afternoon, ladies and gentlemen. And first, let me thank you for inviting me to this great virtual seminar. And this presentation will be based on a joint paper together with Marco Lippi and Brian Anderson. And the slides have been first used at the conference in Zaragoza. This is why Zaragoza is there. And our presentation has a special point of view on dynamic factor models. It is one of these special points of view is that we use the structure of singular AR and AMA systems. It is AR and AMA systems where the innovation covariance is singular as a model class for latent variables. And the analysis of such singular AMA and AR systems has been part of our work during the last 5 years. A related point is that singular AMA systems are generically AR systems as opposed to the non-singular case. So whereas in the non-singular case, AMA systems have a much larger parameter space because of the MA parameters. For singular AMA systems, there's generically an AR representation, which creates a number of advantages, for example, given for estimation. Okay, please, may I ask you to move further? Or could I do it? So, modeling and forecasting of high-dimensional time series is important if cross-sectional dependencies are important. For example, given for improving nowcasts and forecasts for aggregated macroeconomic variables by using disaggregated data. So this is, for example, given, this is an idea which has first been noted by Christopher Sims, who says we should use a great amount of disaggregated data in order to better forecast aggregated data. Marco Lippi used the word big data in econometrics. And why are factor models so important for high-dimensional time series? This is because of the so-called curse of dimensionality. In other words, this is why the traditional approach, for example, by VR, vector AMA models, often suffers from the curse of dimensionality. The reason for this is that if n is a cross-sectional dimension, the dimension of the unrestricted parameter space grows with n squared, whereas the amount of data only grows linearly with n. Okay, next slide, please. And the way out are high-dimensional dynamic factor models. Dynamics is important because we also want to use these models for forecasting. There is early work on factor models for the static case, which has been triggered in psychometrics, and in particular by the question whether one can determine from a great number of items on which measure intelligence, the intelligent factors. Factor models in time series have been developed something like 50 or more years ago. There are the famous papers by Sargent and Sims, by Gewecke and Watson and Engel, and Qua and Sargent. Generalized static factor models have been considered in the two papers by Chamberlain and Rothschild, which appeared in the same issue of Econometrica. the idea of generalized dynamic factor models, the static factor models, is that we weaken the assumption of classical factor models that the components of the idiosyncratic components are uncorrelated. And um, the idea of Chamberlain and Rothschild was to substitute this, to generalize this assumption that the weak, that the components of the idiosyncratic process are independent by assuming a kind of notion of weak dependence. And actually, I still remember Rudi Kalman was also very interested in factor models later on his life. And once I was invited by him to Zurich, and he said to me, you know, we have to, this assumption that the components of the idiosyncratic process are uncorrelated is much too strong, and we have to weaken these assumptions. And whereas, and this weakening has been proposed in this paper of Chamberlain and Rothschild. The main reference for this presentation is a paper called High-Dimensional Dynamic Factor Models, a Selective Survey, which has been published in Econometrics and Statistics, and it is a paper by Marco Lippi, myself, and Brian Anderson. And there has been a lot of work done for generalized dynamic factor models, introducing also this notation of weak dependence in the dynamic case for the idiosyncratic term. And this is a paper by Forni et al., Forni and Lippi, Stock and Watson, Bai and Ng, and Judik and Besaran, Dostjanon and Reichlin, Barigozzi et al., and Pilla Poncela, to mention a few. Next slide, please. So the idea of dynamic factor models is to decompose the observations YTN into a latent part and to a noise part. And the latent part is assumed to show, so to say, the co-movements in the series, and the noise part, for example, given can be interpreted, but not necessarily interpreted, as the measurement errors, or they can be interpreted in a different way, that we have the co-movement and the part of individual movements. And we impose a number of assumptions. One assumption being that the component processes chi and xi are n-dimensional stationary processes. They are centered, and the component processes are mutually uncorrelated. And in this case, if we assume that the spectral densities of the latent part and the noise part exist, then the spectral density of the observations is just the sum of the spectral density of the components. Next slide, please. And we will also impose the assumption that for all n, so n is the cross-sectional dimension, and of course the spectral densities are indexed with n. For all n, the matrix, the spectral matrix of the latent variables is rational, which is the same as saying that they can be, to use a notation from Kalman, they can be realized, or we would say they can be represented as by an AMA or a state space model. So saying f the spectral density is rational is the same as there exists a AMA or a state space model to represent this process. We suppose that there exists an N0 such that from N0 onwards, the rank of the spectral density of the latent variables is independent of N. And we denote this rank by Q. And the next assumption is that the state dimension of a minimal, stable, and mini-phase state space realization corresponding to the spectral density of the latent variables is independent of N from a certain N1 onwards. So this is a kind of assumption that the dynamics doesn't grow, doesn't monotonically grow with kappa N. Next slide, please. So, and then we have, we define weak and strong dependence. We use omega for the respective S largest, omega S sub S for the respective S largest eigenvalue of the Hermitian matrices, the spectral density of the latent variables, the spectral density of the idiosyncratic component, and the spectral density of the observations. So first, there is this assumption, which is close to the assumption proposed by this paper of Rothschild and Chamberlain. We assume that weak cross-sectional dependence of the idiosyncratic process is defined as that the eigenvalues of the first eigenvalues of the spectral density matrices the first eigenvalue of the spectral density matrix, of course, depends on frequency. They are uniformly bounded. There exists a b greater than 0, such that this first eigenvalue of the idiosyncratic component is smaller than b for all n and for all lambda. And analogously, we define the strong cross-sectional dependence of KIT, of the latent variables, and this is again so tied to the eigenvalues of the spectral density of the latent variables. It says that the eigenvalues diverge for the first to the qth eigenvalue almost everywhere in the frequency band. And of course, we have assumed previously that the q plus 1, that the rank of the spectral density of the latent variables is equal to q. So the eigenvalues for q greater than 1 are 0. And one can show that given the process of observations under the assumptions posed here from 1 to 6, that the representation, the decomposition for a given yt into the latent variables and the idiosyncratic variables is unique. Next slide, please. So now we deal with denoising, which is getting rid of the noise to obtain the latent variables from the observations. This has been also called for example, in language processing, the singular sparse decomposition. And it's separating the co-movement from the individual fluctuations. One possible interpretation of the noise is, as I have already said, measurement errors. And the co-movement in the latent variables can be expressed in the following way. As I said already, the latent variables have rank q. So if we consider n larger than q, then the spectral density of the latent variables is singular. And for example, given if we choose a basis, you have to remember that the spectral density of the latent variables is rational. If you choose a rational basis for the left kernel of the spectral density, we have that W of z, the spectral density of chi is equal to 0, implies W of z chi t is equal to 0, meaning that there's exact linear dynamic relations between the latent variables. So co-movement means there's exact linear relation between the latent variables. Next slide, please. So there's another representation which I call the image representation rather than the kernel representation, which is commencing from a singular spectral density of the latent variables. And this spectral density can be factorized into a transfer function which is stable and miniphase. Miniphase means that the VTs here are indeed the one step ahead prediction errors. So where K of z is stable and miniphase, and we obtain that the latent variables are a transfer function, a rational transfer function times the innovations. And we normalize the innovations to have a variance matrix which is equal to the identity matrix. Next slide, please. One sees from this that from an abstract point of view, factor models and errors in the variables and linear errors in the variables models are the same. And this idea has, in a sense, motivated Kalman to go into this research, because there was this, for some time in system engineering, there was this idea of symmetric modeling, which means why are we sure that the inputs are not affected by noise, and it's only the output who are affected by noise. And the approach here, using factor models, meant that there could be noise on inputs and outputs. And there's no a priori distinction required between inputs and outputs. So this was called in system theory symmetric modeling. And the general approach here is mainly structure theory, which is the analysis to understand the relations between the external characteristics of the observations, so the T missing, which are the populations, economents of the observations, and the internal characteristics, which are the parameters of interest. And this is important for subsequent estimation. Yes, please, next. So, as I mentioned before, we have to distinguish between exact and approximate factor models. And for the exact factor model, the assumption is that the spectral density of the idiosyncratic part of the model is diagonal. And then alphabetity, in a sense, can be formulated as, for a given spectral density of the observations, decompose into the spectral density of the latent variables and the spectral density of the idiosyncratic part, because they are mutually orthogonal, it's just a sum. And there are certain problems with this decomposition. One is that not even the rank of the spectral density of the latent variables is fixed given this observation. So we assume that in this decomposition, f high of n has the smallest possible rank. And we can formulate this also in the way in saying it has a maximum co-rank. And for, okay, I should say, this has been considered in detail in a paper published by Wolfgang Scherrer and myself, which was published in Science Journal of Control, and I guess was almost buried there, because it was not very much read by this factor community. Once the decomposition has been granted by additional assumptions to be unique, we also have what Kalman called, we have to realize the spectral density of the latent variables into a unique AMA or state space system. Okay, next slide, please. And this decomposition, which was shown before, of the spectral density of the observations into a part relating to the spectral density of the latent variables, and a second part related to the spectral density of the idiosyncratic part, can be shown to be generically unique if the number of factors is sufficiently small. And there are two ways in showing that the number of factors is sufficiently small. One is the so-called complex Lederman bound, and the other is this what we called uniqueness bound. This says, for example, given if the spectral density of the latent variables is known to have rank 1, we know that every 2 by 2 matrix has a determinant equal to 0 because it has rank 1. And by a suitable choice, one can select the, one should say one thing again. And of course, under the assumptions of the classical model, the spectral density of the observation has the same spectral density, has the same elements as the spectral density of the latent variables, because it's only the spectral density of the latent variables besides the elements of the diagonal, because only the diagonal is, so to say, affected by the spectral density of the noise. Was this clearly put? And this can be used in setting all these 2 by 2 elements. In a sense, they have a determinant which is equal to 0 because the spectral density of the latent variables has rank 1. So all 2 by 2 elements have a determinant which is equal to 0. So this can be used to retrieve from the off-diagonal elements of the spectral density of the observations the diagonal elements. Next slide, please. So in this case, we get a unique decomposition of the spectral density of observations into a spectral density of the latent variables and the spectral density of the idiosyncratic part. And one idea, as I said in the introduction, was to use singular spectral densities for the latent variables, which can be modeled by a singular AMA or a singular state space systems, which, to repeat, says that the innovation variance is singular. And this has been described in detail in a paper by Chen, Anderson, Deistler, and Filler, which was published in Journal of Time Set Analysis. So we write down such a singular AMA system as P of Z chi t is Q of Z Vt, where Vt is the innovation. And this matrix, of course, is square. So it's n times n. And Q, so we consider only the innovations which are unequal to 0. And the Q is n times Q, where Q is the rank of the spectral density of the latent variables. And next slide, please. And we impose the usual assumptions. The stability assumption is that the determinant of P of Z is unequal to 0 for Z smaller or equal, for absolute Z smaller or equal to 1. And we assume also a strict miniphase condition, which is a bit different in this singular case, saying that the rank of Q of Z, this is the moving average part, is Q for all absolute Z smaller or equal to 1. And this guarantees that the steady state solution, which expresses the latent variables as P inverse times Q times innovation V of t. There is an error, so it should there should be no saying that. So sorry, please disregard this part here. It says that if there is a Volta representation corresponding to the spectral density of the latent variables, where the transfer functions are stable and miniphase. Okay, so we factorize the spectral density of the latent variables into transfer functions which are stable and minimum phase. And of course, because f of chi is rational, of course, also the transfer functions are rational. Next slide, please. So we have the usual assumptions that P of 0 is identity matrix, and that P of Z and Q of Z are left coprime matrices. If you don't are familiar with this notation, please forget it. It just substitutes the notion of coprimeness of the AR and MA polynomial in the scalar case. And we have then a minimal state space realization of this rational transfer function, which is of this form here. So it's the latent variables. So the first equation, as in a state space representation in general, describes the dynamics, and then the next equation describes the latent variables as a function of the state. And one should note that there are two different notations of this kind of state space representation. In one there's an epsilon or a WT here in the second equation again, but for us this representation here is more suitable, and because we see that xt is a kind of state, a static factor for the latent variables. And we cannot guarantee whether this static factor is really minimal. And we again impose the stability condition, which says that the characteristical polynomial associated with the first equation here has meaning is stable, meaning that the largest eigenvalue of this matrix F is smaller than 1, and a miniphase condition of this form here stating that this matrix has rank n plus q for all z, absolute z smaller or equal to 1. Next slide, please. And one can easily see that W of t is not only white noise, but it's also innovation. And we can write down the transfer function corresponding to the state space formulation as H Z inverse identity minus F inverse times G. And the latent process is a transfer function of this form here, of the transfer function of this form here, derived from the state space system, applied to the innovations. We should also mention that for a given spectral density of the latent variables, innovations and stable minifair transfer functions are unique up to, so I should say, innovation covariance matrices and stable minifair transfer functions are unique up to pre- and post-modification by orthogonal constant matrices, respectively. So without loss of generalization, we can identify this kind of innovations because they are only related by orthogonal transformation. And also this, the same with transfer function. And so next slide, please. And now I'm going to the kind of usual static factor model where we express the latent variables as a loading matrix L, which is an n times R matrix, and a static factor Ft, which is a factor of dimension R. And we assume that the static factors are minimal, so it has the smallest dimension. And we note that the minimal static factors are unique up to pre-multiplication by a constant non-singular matrix T, and L is unique by up to post-multiplication by T inverse. So this kind of source of non-uniqueness in parameters can easily be, so to say, avoided by assuming that the first R times R block of this matrix L, which is n times R, is non-singular and is equal to the identity matrix. Next slide, please. And this is easy to see that for n larger than n0, we just obtain the same static factors with additional pages in the loading matrix. Next slide, please. And we can derive easily the let me say in short, the static factors from this formula here. And then there is an important point. We write down the dynamics of the static factors relating the static factors to the dynamic factors. So note that Vt is the innovation process and of the latent variables. And these dynamic factors are related to the static factors by a transfer function W of Z, which is stable and miniphase. And we also see from this case that that the static factors may have the same or a larger dimension compared to dynamic factors. And we only consider the case where the number of static factors is smaller than the number of dynamic factors, because this is a typical case. I've come back to this argument before. So next slide, please. So we can write in a certain sense the latent variables as a function of the factor loading matrix multiplied by the static factors. And then we can, in a second equation, express the dynamics of the static factors, so to say, the dynamics of the static factors by an ARMA system. And we assume, of course, that alpha and beta are stable and miniphase, and that alpha of z and beta of z are left coprime. And this is, so they can also be formulated as a minimal state space system by writing down the equation for the latent variables, and the dynamics of the system is again expressed by a dynamic state equation. Next slide, please. So now here comes the motivation for assuming that the number of static factors is strictly larger than the number of dynamic factors. I will mainly concentrate on this argument here. Criteria to empirically determine R, the dimension of the static factors, and Q, the dimension of the dynamic factors, have been provided in many papers. For example, given there are papers by and Inc., by Haller and Liska. Using such criteria, we find in most cases that the number of static factors is smaller than the dynamic, is larger than the dynamic of the dynamic. Sorry, the number of static factors is larger than the number of dynamic factors. I want to relate to the paper by Baragozzi, Lippi, and Luciani. Next slide, please. And of course, if the number of static factors is strictly larger than the dynamic of dynamic factors, for the ARMA system, the matrix P of Z, this is the moving average matrix, is tall. It has more rows than columns, and it's generically zero-free. So let me so to say intuitively explain this notation. So beta of Z is a matrix which has more columns, which has more rows than columns, and so it's a tall matrix. And if we take a Q times Q submatrix and look at the beta of Z, of course, is a polynomial matrix. And if we look at the zeros of the determinant of this submatrix, we see that these zeros generically are compensated by the zeros of other determinants. So this is the meaning one can show in this case that in this case, this was shown in a paper by Brian Anderson and myself. Generically, we have no zeros here. Beta of Z has no zeros. And because of this fact, we can write down an autoregression because autoregressive processes are characterized as processes where the transfer function has no zeros. And we can write it down into an autoregression for the static factors. So I should repeat that typically in this this system is a kind of ARMA system, but because generically B of Z has no zeros, it's an AR system of this form here. And This kind of AR systems have a bit, these singular AR systems have a bit more complicated structure. In particular, it's not sufficient to have the autoregressive matrix as with a leading coefficient equal to identity matrix. And we have to impose in additional assumptions like that the rank of the last AR matrix and of B is equal to R. Next slide, please. So now I'm coming to the next point, which is the generic alphabetity of dynamic factor models. And there's an approach which has been proposed by Dost, Giannone, and Reichling. And this is a paper where maximum likelihood estimation has been proposed. And this has been analyzed in detail, in particular by the paper of by Grozzi and Luciani, and by the paper of Pilar, Poncelar, Esther, Ruiz, and Miranda. And the approach, the core of this approach is to use a state space formulation of a dynamic factor model. Next slide, please. So, and the assumptions corresponding to the state space realization is to assume that the idiosyncratic components are, so we are back to the classical models where the idiosyncratic components are mutually uncorrelated. And we assume that they are of AR1 type. This is not essential at all. And the advantage of the state space formulation is that an EM algorithm of the Shumway-Stoffer type can be used for parameter estimation by means of the Kalman-Smoother. And of course, alphabetity is an important part of the package, and we have shown alphabetity in this case. Next slide, please. So we retain the assumption that the cross-sectional dimension of the time series is larger than the number of static factors, and the number of static factors is larger or equal to the number of dynamic factors. And we have the latent variables and the minimal static factors related by this static factor model, which says that the latent variables are just the product of a factor loading matrix times a static factor. And again, we use the assumption that the number of static factors is strictly smaller than the number of dynamic factors. And this is not an important assumption, as has been argued here, but nevertheless, I will stay with this assumption. And we also assume for simplicity that the remember that the idiosyncratic components are assumed to be uncorrelated, and we assume that every component of the idiosyncratic factor, of the idiosyncratic part is an AR1 model. This can be easily generalized. So an AR1 model of the form psi IT is equal to delta I psi IT minus 1 plus eta IT. And we assume stability, and we assume that we have cap n, of course, such autoregressions, and that the chi IT are mutually uncorrelated and zero mean white noise processes, and also uncorrelated with the process YT driving the factor process model. Okay, next slide, please. So under these assumptions, we can construct a state space system, defining the state as the, so to say, the present and the delayed until a delay of t minus p plus 1 of the static factors. So we have the state consists of the static factors and of the innovations for the latent processes. And this gives a model of this form here, where we have in the first block line the matrices A1, A2, and AT P tilde minus 1, which are relating to the vector autoregressive model. And then we have this kind could be called a companion form up to here. And then we also have the parts relating to the idiosyncratic component. Okay, next slide, please. So this is just explains that we have stacked the vector of the autoregressive coefficients for the idiosyncratic part, for the idiosyncratic components, and then we have a kind of going back to the slides before. Then we have to the sorry again. Then we have this kind of idea that we generically we have for the static factors, if the number of static factors is strictly larger than the number of dynamic factors, we have rather than an AMA system, an AR system generically. And this writes down the AR system for the static factors. Was this clear up to now? So I write down, so I have this separation. I have static factors, and I explain in addition the dynamics of the static factors. And because of rationality, this is in general an AMA system, but in particular, if the number of static factors is strictly larger than the number of dynamic factor, it's generically an AR system. And I have, so to say, an AR polynomial of this form here. I have the identity matrix, and then I have the matrices weighting the lagged static factors. And of course, we retain the stability requirement that this system is a stable system. Next slide, please. And this says what I have mentioned already before. So we have to ensure that the static factors are unique. And this is done by assuming that the first block of the static, of the first square block of the loading matrix corresponding to the static factors is equal to identity. And we should also assume that generically the quantities delta inverse are not zeros of this stability equation here. And the first step in establishing generic alphabetity is to explain how the separation of common and idiosyncratic components can be achieved. And this is done, what I have already explained before. This is done from the observation that because we are in a classical factor model, that the off-diagonal elements of the spectral density observations are the same as the off-diagonal elements of the spectral densities of the latent variables. And this is used to decompose Fy into F chi and F psi. So the spectral density of the latent variables and the spectral density of the noise part. Next slide, please. So we suppose, as I have already mentioned, that the spectral density of the noise part is diagonal, and that n, the cross-sectional dimension, exceeds 2q. Q is the a rank of the spectral density of psi. And so this idea, I explained once again, is to look at submatrices of dimension q times q and their determinants. And this is used to separate, so to say, to obtain also the diagonal elements of the spectral density of the latent variables. And so the idea is, if we know that the spectral density of the latent variables has a rank q, so we selecting q times 1 times q times 1 submatrices of the spectral density of Fy, which are, so say, non-necessarily contiguous row, and which contain just one diagonal element in order to retrieve these diagonal elements from these settings that determines equal to 0. Thank you. Next slide, please. Next slide, please. So the next step in establishing generic alphabability is to construct the real value parameters lambda and A1 and AP, beta. So you know, lambda is a factor loading matrix for the static factor model. A1 and AP are the autoregressive weightings of the past of select static factors, and B is corresponding to the extremely simple part of this matrix on the right-hand side of the model, of the R model explaining the dynamics of the static factors, and delta is the vector of coefficients in these AR1 models for the idiosyncratic part, and these are the idiosyncratic innovations. This is the variance of the idiosyncratic innovations. And for given integer value specification parameters R, Q, and P tilde, so to say R is the number of static factors, Q is the number of dynamic factors, and P tilde is the maximum lag in the autoregression for the static factors. And for a given spectral density F chi, or equivalent for the second moments of chi d, this is done as follows. We look at this equation here, and L is uniquely determined by this factor loading. So for a minimal static factor, the factor loading matrix is uniquely determined by assuming that the first block of L is identity matrix, and then the transformation uniquely determines the second moments of the process of static factors. Next slide, please. So, and if you remember the formulation of the state space formulation of the dynamic factor model, then these parameters here, which are weighted in the autoregression by the legs of the static factors. So by the so the A1 corresponds to the static factor legged by 1, and A B tilde corresponds to the static factor legged by P tilde. And if we assume that the covariance matrix by these stacked static factors is larger than 0, then we can uniquely retrieve the parameters A1 to AP from this autoregression. Next slide, please. And after having done this, we can obtain the latent, the spectral density of the idiosyncratic part from the spectral density of the observations and the spectral density of the latent variables. In this way, we can obtain the parameters which are the autoreceive coefficients for the noise part. And this is the innovation of the noise part. And it should be noted that the assumption before, may I ask you to go back? This assumption here, that this matrix of the stacked static factors is non-singular. Please, next slide. This is equivalent to controllability of the state space system. And due to our assumptions, this is also fulfilled, as I don't want to go into details, if we have that the number of static factors is the same as the number of dynamic factors. So if we approximate, so to say, the AMA process by an AR process. Okay, next time. Next slide, please. So I'm coming to the summary. We look at generalized rather than partly, rather than exact linear dynamic factor models. The motivation for looking at generalized factor model is that even if we use this state space representation, there is a paper by Doss, Giannone, and Rechlin, which shows that even under this misspecification, that we have a general rather than a classical factor model, meaning if we have a weak dependence in the noise spectrum rather than diagonality of the spectral density of the noise, that the parameters of the underlying system are consistently estimated for n going to infinity. And so we have derived a structure theory, this analysis of the relation between the population second moments of the observations and the parameters, which we claim is important for understanding estimation. We have, so to say, decomposed the problem into two parts. One is modeling of by static factors, and then is modeling the dynamics of the static factors. We allow for weak dependence, for weak cross-sectional dependence in noise. And there's another approach which has been more or less, which comes from this paper by Chamberlain and Rothschild for the static case, and which has been generalized by Marco and co-workers for the dynamic case, which uses a completely different approach. It is using denoising by annihilating sequences, which lead to identifiability of a state space representation. Thank you very much for your patience.
Okay, thank you very much, Manfred, for that wonderful presentation. Let me stop the recording, and we can move to the question.